Hi students, this is VLSI Design. Now we are going to discuss about non-ideal IV characteristics presented by our Subhasharmini Devi. In this topic, non-ideal IV characteristics, after completion, students will be able to explain the electrical properties of MOS transistor and then explain the body effect and its effect in MOS device. Why we are going to non-ideal IV characteristics means the drain to source current value of an ideal IV model neglects many effects that are important to device with channel length below 1 microns. That's why we are going to discuss the non-ideal IV characteristics. Some of the characteristics are velocity saturation and mobility degradation, channel length modulation, body effect, subthreshold condition, junction leakage, tunneling, temperature dependence and geometry dependence. Now we are going to see about the velocity saturation and mobility degradation. First one, velocity saturation. In this topic, at a high lateral field distance means lateral. It is carrier velocity increasing to the linearly with field distance. That means E is equal to VDS divided by L. VDS means drain to source voltage and the L means length of the transistor. This is called the velocity saturation. If carrier scatter of atoms in silicon lattice, velocity reaches Vz. In the electrons, 10 to the power 7 cm per second, holes 8 into 10 to the power 6 cm per second. In the better model, we are having velocity is equal to mu effective E divided by 1 plus E by EC. If electric field, that means E is less than critical field, that means EC. Then Vsat is equal to Vsat means saturation velocity is equal to saturation velocity when it will reach the Vsat means electric field greater than or equal to critical field EC. Then EC means already we know about the 2 Vsat divided by mu effective. Next one, channel length modulation. The reverse biased PN junctions from a reflection region. Then region between N and P with no carriers. Then width of deflection LD regions grows with increased reverse bias. Here we are having it is the original length of the channel and then after the deflection region we are having the L effective is the channel length of this transistor. This is the deflection region width. Then how to find the L effective means just subtract from original length to the deflection region length, then we are having the L effective means L effective is equal to L minus LD. Then shorter L effective gives more current. IDS increases with VDS and then even in saturation. Next, channel length modulation of the IV characteristics means if IDS is already discussed in the previous sections. IDS means drain to source current is equal to beta by 2 VGS minus VT the whole square into 1 plus lambda VDS. VGS means it is the gate to source voltage. VT means threshold voltage. Then VDS means drain to source voltage. Then lambda means channel length modulation coefficient. It is the not feature size and empirically fit to IV characteristics. Next one, body effect. Body is the fourth transistor terminal. Already we know that if the three terminals of the transistor is gate, drain and source. The fourth one is body. It's already all are know the transistor models. Then VSB affects the charge required to invert the channel. Increasing Vs or decreasing Vb increases the threshold voltage, that means Vt. Vs means nothing but source voltage and Vb means it's a base voltage. Next, Vt is equal to Vt naught in plus gamma into root of pi s plus Vsb minus root of pi of s. Pi of s means surface potential at threshold. Pi of s equal to 2 into Vt ln into Na divided by Ni. Depends on doping level. Na means it's depend on doping level. And intrinsic carrier concentration is denoted in Ni. Gamma is the body effect coefficient. Body effect coefficient is the gamma means T of Ox divided by epsilon Ox root of T2Q epsilon Si into Na. TOX is nothing but oxide thickness. Epsilon OS means it's nothing but oxide permittivity. Then we are know about TOX divided by epsilon OX equal to 1 by COX. That's why we are having the COX. Epsilon OX is nothing but it's a permittivity of oxide, and then TOX means oxide thickness. Next, subthreshold leakage. Subthreshold leakage. It is the leakage potential when VGS is greater than VT. That means VGS means gate to source voltage is greater than threshold voltage, means we reach the limit is IDS equal to IDS naught e power VGS minus VT naught plus neta VDS minus K gamma VSP divided by neta into VT into 1 minus e power minus VDS divided by VT. Here, IDS naught is equal to the current at the threshold and IDS naught is equal to beta VT square into e power 1.8. Next one, junction leakage. Normally, in the junction leakage occur in the some leakages. That leakages are ordinary diode leakage, band-to-band tunneling, gate-induced drain leakages. Then reverse biased PN junction have some leakage. ID is equal to IS into e power VD divided by VT minus 1. At any significant neglect diode voltage, ID equal to minus IS. IS only depends on doping level. IS is nothing but source current, the area and perimeter of diffusion regions. Next, ideal IV characteristics are already we know this one. What are the regions of the transistor and what is the values of current from each region. Next, temperature sensitivity. It's the temperature sensitivity. If temperature increasing reduces the mobility and reduces the threshold voltage. If current is on decreasing with the temperature and current is off in increasing with temperature. That graph is shown in here, voltage and the temperatures graph in this graph. Next, last one, the quiz question of this topic on non-ideal IV characteristics. Derive the noise margin for CMOS inverter.